Hello everyone, today we're going to be talking about evaluating limits algebraically. So in the past, we've evaluated limits when we are given a graph, when we are given a table. We can do direct substitution and even use some of the properties of limits, right? And I'm going to show you why for some problems you might need to do a little bit more work. So if I were to try to use some of the methods we've already done, like direct substitution into this limit as x approaches -1, I could try to plug in a -1 into my problem, but right off the bat, I'm noticing that my denominator of -1 plus 1 gives me 0. And we know that anytime this happens, this is undefined in math, right? Instead, I need to use algebra to manipulate the function and try to do some factoring. So in my numerator, I can see that I have a quadratic that does not have a coefficient of 1. The coefficient is 2. And so I have to be able to factor this quadratic. And I know I've said it a couple times already, but you gotta know how to factor these quadratics that do not have a coefficient of 1. Whether you like to use factoring by grouping, or I know some students use the tic-tac-toe method, so whatever works for you. I start by doing a big X to find my two B values, and then I personally use factoring by grouping. And so with factoring by grouping, and you can always YouTube this to get some more practice, I copy down the problem. Okay, but instead of my B value being -x, I'm going to replace those B values with -3x and 2x, because -3x plus 2x would give me the same thing as -x. So again, my B value changes to be these two values I got from my big X. And now I use my factoring by grouping, where I try to factor these two terms and the last two terms. So looking at the first two terms, I can see that they both have an x in common, but that's about it. And then the last two terms don't have anything in common, so I can factor out a 1. And so looking at this expression as a whole, each term has a 2x minus 3, so I'm going to factor the 2x minus 3 out, and what's left over is x plus 1. So really, my expression of 2x squared minus x plus 3, or minus 3, can be rewritten as these two binomials once we are done factoring. And so we said we had a denominator of x plus 1, and I'm still taking the limit as x approaches -1. But now I can factor out the x plus 1s on the top and the bottom. These are the same. X plus 1 on the top and x plus 1 on the bottom are going to divide. And so now I'm left with evaluating the limit of 2x minus 3 as x approaches -1. And I can try to do direct substitution now. So I'm going to say 2 times the -1 minus 3 gives me -5. So I know that the limit of the entire function prior to factoring or after factoring, because those are equivalent expressions, is equal to -5. Okay, there we go. And so not only can I now find the limit, but I can also observe what is happening at the function. So what was I able to factor out? Okay, in factoring out x plus 1, the function went from being undefined when we plugged a -1 to actually giving us a value after I take away that denominator of x plus 1. And so whenever this happens, what we can do here is take our denominator of x plus 1, right? And we set this equal to 0. And so I know that at x equals -1, at this location, I'm having some kind of discontinuity that's causing my function to say undefined. And so I'm going to say that I have a removable discontinuity . And we said the value was x equals -1, and the y value would be whatever your limit value is. So in this case, I have -5. So I know that there's a hole specifically happening at -1, -5. And I'm going to switch over to Desmos to show you. I'm going to go ahead and copy our entire function into Desmos to see what's happening here. So I'm on my Desmos screen, and I already typed in the original function 2x squared minus x minus 3 over x plus 1. And I also typed in the expression that we got after we factored and divided, which was 2x minus 3. And if I toggle the colors on and off, you can kind of see that these expressions are equal, right? 2x minus 3 is the same as that function because they are equivalent. And according to our algebra, we predicted that there is going to be a removable discontinuity, which is also known as a hole, which we learned about in pre-calculus, at specifically -1, -5. So I'm going to trace my function, and I'm going to go down to -1, and I should get undefined. Oh, there it is, at -5. So at the point -1, -5, Desmos is saying undefined, and that means that I have a hole specifically at that point. Everywhere else, it's assumed to be continuous, and there is a point except at -1, -5. That is a removable discontinuity, which again we can call a hole, the equivalent. So coming back to our notes, we're going to go ahead and try out the next couple problems. But remember, the expectation is not only to find the limit, but also to state if there is a removable discontinuity happening at the function. Okay, so here I forgot to mention that for this particular problem, there's a little bit of an error. This should be +3. Sorry, that makes a little bit more sense, because now if I were to plug in 3 into the denominator, I would get, again, that problem of division by 0, which is undefined. So we need to do factoring before we can try to plug anything in. And so I have x cubed minus 27. And because x is being cubed, I'm thinking, maybe this can be a difference of cubes. Does 27 have a perfect cube? And yes, it does. I know that 27 is the same as 3 cubed. And so in the same way that there is a difference of squares, and I know that the difference of squares is a lot more popular, right? If I have a squared minus b squared, that's the same as factoring it into a minus b times a plus b. Well, very similarly, we have some shortcuts when we have the difference of squares. And so the difference of squares formula, and you want to, again, have the difference of squares and the difference of cubes formulas kind of written in your notebook, if not memorized. The difference of cubes formula is a cubed minus b cubed. And that factors to become a minus b, a squared, plus a times b, plus b squared. Okay, so in order to move forward, I need to evaluate what is a and b in my problem right now. Well, I can see that x is being cubed, right? And so I'm going to say that that's going to be my a. And then 3 is being cubed, so that's going to be my b value. So anywhere in this formula, wherever I see a, I'm going to be plugging in x. Okay. And in this formula, wherever I see b, I'm going to be plugging in 3. So b becomes 3, 3, 3. There we go. And now I can simplify a little bit. X cubed stays the same. X times 3 is 3x, and then 3 squared is 9. Okay, so that's my difference of cubes. So that means that x cubed minus 27 is now going to be rewritten into all of this that I just stated down here. This is the equivalent factored form of x cubed minus 27. Okay, great. Now, what is the same on the top and the bottom? X minus 3. So these factor out, and I'm left trying to evaluate the limit as x approaches 3 of x cubed plus 3x plus 9. And now I can go ahead and try to do substitution. So I'm going to plug in directly here. I'm going to get 3 squared plus 3 times 3 plus 9, which is going to give me 27. So I know that the limit of x cubed plus 3x plus 9 as x approaches 3 is 27. So that's my limit. And also, let's remember, where is there a removable discontinuity? So if I were to take my denominator of x minus 3, right? If I take this guy, x minus 3, and I set it equal to 0, that's telling me that I'm going to have a removable discontinuity at the value of 3. So I'm going to say, in addition to our limit, we also have a removable discontinuity. I'm going to put the coordinate, remember, because this is a hole, a point, at 3 comma, and the y value is our limit value, which is 27. So again, if you were to graph this, function, you would see a hole, an undefined point at 327 if you go on Desmos and graph it. All right, we're going to be looking at example number 3 now. And I have x to the power of 10 minus c to the power of 10 all over x to the power of 20 minus c to the power of 20. Now, just looking at it at first glance, this problem may be a little bit tricky because we can't really clearly see what needs to be factored. But this is where you have to use your rules of exponents. So I'm actually going to rewrite x to the power of 20 and c to the power of 20 as being squares of x to the power of 10 and c to the power of 10. So if you recall from the rules of exponents, if I raise a power to another power, then I would just need to multiply 10 times 2, and that gives me my 20. So that is why I can rewrite x to the power of 20 as this. These two are the same, okay? And so I'm also going to do the same thing with my c to the power of 20. I'm going to say c to the power of 10 to the power of 2, okay? And when I do this, I can see now that this is a difference of squares. I have a squared value subtracted by a squared value. So I'm going to use my difference of squares formula that I was talking about earlier that says that if I have a squared minus b squared, this can factor to be a plus b times a minus b. So what is being squared? My square is x to the power of 10. That is what's being squared. And c to the power of 10, that is also being squared. So that's going to be my a and my b value. And so if I plug them into this formula, a is x to the power of 10 plus b is c to the power of 10. A is x to the power of 10 minus, again, my b is c to the power of 10. So I can rewrite the denominator as that factored form. So I'm going to rewrite this. We're going to say the limit of x to the power, x approaches c, of x to the 10 minus c to the 10 all over x to the 10 plus c to the 10 times x to the 10 minus c to the 10. Okay, now what is the same on the top and the bottom? And you know you did something right when you're factoring, when things begin to cancel from the top and the bottom. And so if I were to rewrite this, all I'm left with is x to the power of 10 plus c to the power of 10. But be careful because that's in the denominator, right? That's in the denominator, so it needs to stay in the denominator. And if you have to divide by 1, do that so that it stays in the denominator, okay? So now I can go ahead and try to use direct substitution. And I'm going to get 1 over x becomes c to the power of 10. And since I have the same c to the power of 10 plus c to the power of 10, that's the same as 2c to the power of 10. So I'm going to say the limit of all of this crazy stuff winds up being 1 over 2c to the power of 10. Do I have a removable discontinuity? Yes, I do. I have a removable discontinuity at c, comma 1 over 2c to the power of 10. Okay, so now I want you guys to try these out on your own. They're extremely similar to the ones that we just did. I really want you to pause the video and try them on your own. I am going to quickly solve them on my screen, and I'm going to resume once all the solutions are there so you can... Okay, everyone, go ahead and feel free to pause and compare your work and compare your answers. This is a solution to number 1. This is the solution to number 2. Here is the solution to number 3. And lastly, number 4.